So in the previous sessions, we have been discussing regarding the optimizations, and we have covered a bit of material, covered a bit of basics. But in order to understand optimization really well, so what we should do is we should know some requisites, know some terminologies that will be frequently used and stuff like that. So I'll just briefly brush up these things so that in the subsequent lectures when we discuss about optimizations, you will have no problems in understanding that. So as of now, you understood derivatives. Again, just you understood derivatives. So if I ask what is the derivative, so derivatives, these basically give us the instantaneous rate of change. Instantaneous rate of change. Instantaneous rate of change. Why am I saying it again and again? Because this is so important. This understanding this rate of change is really important. Why is it important? Because you are in your daily life seeing what is the impact of one thing or the other thing, how rapidly or how slowly is it changing. So that's what derivatives give you. Okay. So if you have a function, for example, f of x means the function is in one variable. So let's suppose we have this 2x square plus 3. This is the function. So if I say if I make a slight change in this x, so what will happen to the function in general? I told you in the previous session as well that each function basically you can graph it and you can graph it, and these functions basically are some real world processes. So if there is a real world process, you can mathematically model it into a function. So what happens to that function, that is basically reflecting the real world. So let's suppose this is a function which simulates a real world process. It says something about some real world process. So in that, the x is the process, x is a feature which impacts the process. For the real world example, let's say it's weather. Okay, weather is actually what is happening your outside the environment, what's the temperature. That thing is actually a physical phenomenon. It's a physical process. So we try to model that physical process into mathematics by using the mathematics. So I told you that let's suppose we have a feature x. Let's suppose this x we call it the previous day's weather. The assumption here is that the previous day's weather is dependent on today's weather, and I am telling you that the weather today is dependent on previous day's weather by this equation. So I'm trying to model, I'm trying to predict something. Before that I have to model it. I model it by this function. So what I'm seeing is I am telling you, if I change this previous day's weather, if I change it a slight bit, so what is the change in today's weather? So whatever change will happen to this variable, this x, so what is the effect, what is the overall effect that will happen to this? That's what is derivative. So derivative basically gives you the rate of change. So what will happen if we slightly change something, what is the impact it will have? Okay, so here we denote it by f dash of x. So you know how to take the derivative of this. This is 4x, and this is the constant derivatives, basically 0. So this is how will it change. This gives me the rate of change. But sometimes what we have is sometimes we have functions which are multivariable. So there are a lot of variables. So there is not just one variable. So there are variables in different directions. Like you saw here, we had, let's suppose, one variable and the function was like, let's suppose this, something like this. So here if we want to find the rate of change, we were just differentiating it like that, and we're trying to find what's the rate of change. But what if we had a multivariate, we call that multivariate function. If we have a function which has multiple variables and there are different, and that's what machine learning is basically. So there will not be only one feature. So there will be a lot of features at least. So that we have, for example, if I show you a picture of this multivariate function in which we have a lot of things, I'd like to show you that. Just wait a while. So I'll just share the screen. Let me show it to you. Where is the Chrome? Here it's. Are you able to see it?
Yes, sir.
So, so if you see this function, so this is, for example, a three-dimensional function. We have an x, we have y over here, we have z over here. So first, let's see the 2D functions. Let me first show the 2D functions. Let's suppose. Here, if you see, we have a 2D function. Here it is. So here, if you see it here, we have this x-axis and we have this z-axis. Let's suppose this z-axis is not there. Let's suppose that we have only 2D function. So the functions that we have been plotting, x square. So even we had the tool. If you remember that tool, we had uh, for the function plotting. What was it? What was the name of that? Desmos. So Desmos calculator, we had that tool, Desmos. If we just search for that, and we can graph any function, graphing calculator, if we see it here. So if I have to graph x square, so this is the function. So over here you can see that this is the function of x square. So this basically is in one variable. So you can just change the x and you can get the value. So if the function that I wrote is 2x square plus 3. So this is the function 2x square plus 3. This is the function 2x square plus 3 is the function that I wrote. This is the function. Okay. So now if I want to see the rate of change, if I want to see its rate of change, I said that you have to take the derivative of this. So in order to take the derivative, and I want to see the rate of change. Sorry if the screen is not visible. So this is my function. This is my function 2x square plus 3. So I said if I want to see how does this function change with respect to x, what will I do? I'll take the derivative. So derivative du by dx of this 2x square plus 3, that is basically equal to 4x. So now I'll graph 4x. So what will this 4x show me? It will show me how does this change. So I'll give 4x. So 4 multiplied by x. So this is the rate of change. So this line over here gives me the rate of change. How this function changes. This 2x square plus 3 changes. So this is the change. This is the function of change that it gives me. So now this is in terms of only, like we have only one variable. If you see, we have only one variable, that is x is changing. So what if I have a function which is in two or more variables? So let's suppose I'll try to draw a function here, for example 2x plus, and then I'll write y square. Let's see. Let's suppose I'll write this and I'll try to see. Now you cannot see a function because you can saw this red circle over here trying adding equal. Like there are a lot of these variables. It cannot cope up with these variables. So there has to be there are different ways by which you can create those graphs. So is it clear? Like I cannot draw the graph with by using this Desmos simple, like where I had this 2D graph in which I had only one variable. When I involve more than one variable, I need some additional tools. So how
Yes.
these graphs will look like, I'll show you that. These graphs will look like this. So this graph here over here, if you see it, this graph has at least, like it is dependent on, it is in three, the equation is in three variables, but two variables are there which are dependent, which are independent variables, iv. So let's suppose we call these variables as x and y, and z, this is the value, and in the previous we had the two variables. Y was our dependent variable and x was our independent. X, because x to x we gave values, and y, the value came out because it was dependent on x. So here if you see this, graph, so there are there are at least now two values, x and y, on which this z depends. Okay. So if I change this x and if I change this y, I want to see what is the change in z. So now if I have to write an equation for this, let's suppose I have an equation for this which looks like this. So I have an equation 2x1 square plus 4y1 cube, 4x2, let's suppose x2 cube. So now the thing, it depends on how many variables. It depends on two variables. Let's suppose this is some z. So this function now depends on the two variables. This is the first variable and this is the second variable. What was the meaning of differentiation? What was the meaning of differentiation? It was, the meaning was rate of change. You have to see the instant rate of change with respect to one variable, as we had in one variable, so it was one variable. Now this concept goes sort of like we have to adapt to that concept. The first thing is we had one variable, and if we want to differentiate with respect to that, we're saying that the differentiation means the instant rate of change with respect to that variable. Now the question is that if I have more than one variable, let's suppose here my z depends on x1 and x2. Now I want to see if I change x1, what will happen to z? If I change x2, what will happen to z? But this is a question actually. So we can also again use differentiation. So what we'll use is, we'll use what we call the partial derivatives. So we'll use the concept of partial derivatives. So what is the partial derivative saying? Partial derivative says when you want to see the change, what is the change if I change this x1? What is the change in z if I change this x1? So you can do one thing. You can take this dou z by dou x1. So this means what is the change in z with respect to x1? If I make a slight change in x1, so what will be the effect on z1? So this is given by this. So how to compute this? It says only consider x1 as variable and rest consider as constant. Okay. So here if we want to take a derivative of this, so we'll write partial derivative of z, that means 2x1 square plus 4x cube. So now you know that x2 is constant. This is constant. This 4 is constant, x2 is constant, this is constant. So what will be the answer for this? We'll only take the derivative of this. This will be 4x1. This will be 0 because now we took it as constant. So this I can say is the rate of change or inside rate of change of z along the x1. Okay, so there will be a change in along the x1. If I now want to compute partial derivative of z with respect to x2, so what I'll do is partial derivative with respect to x2 of 2x1 square plus 4x 4x2 cube. So now whole of this is constant. This is equal to 0. This is constant. Now for this it is 12x square, 12x2 square. So this over here and this over here. Now we computed this partial derivative in two directions. We computed in x1 direction. If I change x1, what will happen? If I change x2, what will happen? So this is called as partial derivative. You can also now take the combination of these. So if you want to see, if I make some change in x1, x1 basically will be in some direction, x2 will be in some direction. So if I want to make some change in the combination of these directions, so I want to see the change. For example, when you had only one variable, so you had one choice. So when your equation was in one variable, let's say x1. So you are making change along this x1 and seeing how did the function behave, what is the rate of change. So now you have this, now you have like this. This is our x1 and this is our x2. Now you can nudge these two values. You can change x1, you can change x2. You can only change x1, you can only change x2. You can change both. You can change a lot of things. So all these things, if you change combination of these things, that will lie around here, that will lie around here, that will lie around here. Okay, because you are now changing the combination of these things and you want to see the impact that it's having on the function. Okay, that is called as gradient. So now we'll see the gradient. What gradient means. If you are clear with partial derivatives, so what's the meaning of partial? Is it clear for you? What is the meaning of partial derivatives?
Yes, sir.
For this, you must understand what is derivative, and then we move to the partial derivative. And from the partial derivative, I'll move to the gradients. Okay. Now I'll move to gradients. What I say gradient means, now you have an equation which has multiple variables, or a function which is governed by multiple variables. Usually, all the physical phenomena mostly they are governed by multiple features, multiple factors. That's when we model these problems. So there will be multiple variables involved. So for that, you have to take the partial derivatives. So now gradient is sort of taking all these partial derivatives and collecting them into a vector. So what is a gradient? Gradient is a vector that is made of all the partial derivatives of the function. The simplest definition, you can get into more mathematical details though. But what I'm saying you, let's suppose we had these functions x1 and x2 were the two variables on which the function depended. So what I'll do is I'll now have a vector like this. So I'll say partial derivative with respect to x1 of that function f. Let's suppose f is this and it is dependent on x1 and x2. And I'll say partial derivative of f with respect to x2. So I collected these partial derivatives into a vector. Now this I'll call as gradient. So gradient is represented by del, sometimes reverse del. Del f is the gradient. So this is called as gradient, or we'll sometimes represent this as gradient of f. So nothing, you are doing nothing special. What you are doing is you are differentiating this equation with respect to x1 first, then with respect to x2 first separately. Then taking the partial derivatives and collecting them into the vector. So is the gradient clear? Is the gradient clear?
Yes, sir.
Yes,
Nice.
sir.
So now what I'd like to tell you guys is that we'll go into the higher order derivatives. What is a higher order derivative? If you differentiate some things multiple times. So if you are differentiating one time, you will get something. If you are derivating some other time, first we'll see the physical meaning of that also, and then we'll see what is the implications of that thing, and then we'll move on to the convexity and different things. So you are done with the gradients. You know what's the partial derivative. You know what's the derivative. And now what I want you to give is what is the meaning of higher order derivatives. Higher order derivatives. Again, to reiterate, consider math as a tool. Do not think we have to mug up the mathematical formulas and things like that. Math is a tool that tries to describe reality. So if you have describability, you use maths, you model the things with mathematics, and then you try to see what will happen to the mathematical equations, and that will happen to the physical phenomenon. So if you are throwing a stone and you know it will follow a projectile motion. So for example, if I am on the ground and I throw stone from here, so you know it will go around this. So now you want to see where will it land. This is a physical phenomenon, and you use mathematics to model the problem, and the laws of physics will be there, and by those you'll be able to compute how much distance will be traveled by the stone, or by the or maybe how much maximum distance will it attain, or things like that. So now I'll tell you what higher order derivatives are. So if you have a function f of x, so if you take a derivative, let's say f dash of x. I know there are different notations. It can be written as like this: d by dx of f, or d by dx of fx, and now I'll write it like this. Okay. So if I take the single derivative, so this gives me change in the slope, or this gives me what the rate of change. So if I have a function like this, let's suppose I have a function like this. So this is the derivative. So this slope will sort of change everywhere. So here it will change, here it will change, here it will change. So everywhere it will change. So I want to capture that change. This is that change in that. So if you now see, for example, if you have a function like this, okay, if you have a function like this function is cos theta, because cos 0 is equal to 1 and cos 90 is 0. And you know the derivative of cos theta is, what is the derivative of cos theta?
So minus sin theta.
Minus sin theta. Minus sin theta means that it will be like this. Minus sin theta is this. Okay. So derivative basically means if you change this, if you see the slope over here, so if you take this, if you track this line, first you see slope is 0, so that's why it's reflected over here, the value is 0. The slope slowly first it decreases, that's why the value decrease until it becomes 0, till it becomes 0 over here. Okay. And then it'll for example it'll become the least over here, that's still there, and again it'll start increasing. That's why the rate of change is described by this rate of change. So if I show you these things also, if I show you the graphically, because these graphs may be inaccurate, I want to show these graphs onto that tool which we are using, Desmos. So I want to show you that. So I want to first show you cos of x. So I'll just show you this is cos of x. Okay. So now you know that differentiation of cos of x is equal to negative sine of x. This is what it shows. This green is sine. This is cos. So this green graph shows you that what is the change in slope. What is the change in slope that is happening? So if you drop a tangent over here, so tangent onto this one. If you drop this tangent onto this one, so you know that it will be a straight line. So you know rate of change onto this point 0 is basically 0. That's what this graph is showing. Okay. So if you see the slope, or let's suppose for example here, okay, so this is actually the rate of change is decreasing, so you will get a decreasing thing over here, you see decreasing. So now if you see from here it was decreasing, and it will start increasing. So from here it will start increasing, that's why the values start increasing from here. Okay. So if you just focus on the slope, what will happen to the slope if there is a line, and if this firstly initially the slope was 0 on this point, the slope basically is the tangent of this line, it is 0. Then it started decreasing, and then it started increasing. That's what this graph is showing, that's what this green graph is showing. Initially it was 0. Okay, start decrease till this, start increasing till this point, and then start decreasing like this. That's what the behavior of cos function is, and this is the behavior of the change of cos function. How does the slope change of the cos function? That's the meaning of derivative. Okay. And if you take the reverse, if we have to take sin x, you know it's equal to cos x. This is the function, so this is the derivative. Okay. So as we had if we have a function, let's suppose x square, so you know this is x square, so how will the slope change? This will give 2x. This is how the slope will change. The slope basically will change like this if you take the x square. Is it clear?
Yes, sir.
Is it clear what these graphs show? So now the topic is the double derivative. If I take the derivative twice, so what will happen to that? If I take derivative thrice, what will happen to that? So now I'll tell you, if I am changing distance, so I said distance is dependent on time. What will happen if I change a little bit of time, and I'll see what will happen to the distance? You know, it will either increase, or it will remain constant. So distance per unit time, what do you call that? Distance per unit time, you call it as Speed.
Yeah.
That's what, if somebody gives you distance, so what you can do is you can take derivative of this distance with respect to time, so you'll get speed. Okay, so that speed, what is the meaning of speed? Speed means rate of change of distance, how much is distance changing when the time changes. Okay, and then if you again take a derivative of speed, so derivative of speed with respect to time, so this gives you the acceleration. Acceleration means how fast are you going. So are you accelerating? Are you decelerating? Are you putting brakes on your bike or maybe a motor vehicle, whatever you have? So are you putting a brake on that? Then it will decelerate. Okay, or if you are putting your foot on maybe accelerator, then it will accelerate. Okay, that's what double derivative says. We can say first derivative of distance gives us what? It gives us speed. And double derivative of distance or derivative of speed gives acceleration. So if you are changing speed, sometimes speed is high, that means you are accelerating. If speed is less, if you are decreasing your speed, that means you are decelerating. So derivative of speed is equal to double derivative. So we write it like this: d2 square of d2, something like this, of distance, which is equal to derivative of speed. This gives us acceleration. And if you again take derivative of this, the third derivative, let's suppose d by dt cube of speed, we call it something called a jerk. It's named at this. The first, if you take the derivative of distance, it gives us speed. If you take derivative of speed, it gives acceleration and things like that. When you basically want to see, so what happens if I change time with distance, it will give you speed. So if I now measure, okay, how is speed changing with time? So it is increasing, decreasing. What will happen to speed? That is acceleration. Now if I see how is acceleration changing with respect to time, that gives me jerk and things like that. And they have physical meanings. Is it clear how, like, what is the meaning of these higher order derivatives? Okay, so the takeaway I'll write over here is try to find meaning. So if you find meaning in the things, that this will sort of change your perspective about the life. So you now ask right questions. It's not difficult to come up with the answers. The difficult part is to come up with the right questions. The people who came up with the right questions, then the finding part was maybe difficult, but it was not that difficult finding a right question. That's why whenever you are studying something, ask a question. Why are you studying it? What is the implication of this? What is the meaning of this? So if you have that framework of study, if you study in that manner, it will be really good. So now you sort of understood what is the meaning of these higher order derivatives. So you can take derivative of one thing. So you can take df by dx. This is the single derivative. The double derivative will be written like this. Triple derivative will be written like this. You can take any order of derivatives. Okay. So if this function is distance, so this will be speed. So this will be. So here, if this is f is distance, if f describes distance, so df by dx, this will describe speed. So this will describe acceleration, and this will describe jerk. Okay, in a similar fashion we can take these double derivatives. Now I just want to focus you guys on this double derivative. Let's suppose I have a function like this. I have a function, x square's function is like this. Let's suppose I have a function like this. Okay, this is a function. Maybe I don't draw it really good, but this is a function. This function is x square, some x square. So if I take the derivative of this d by dx of x square, so this is equal to 2x, that so it will be a line sort of thing. So if you see this point over here, so here the function attains the minimum value. Here the function attains the minimum value. If it attains the minimum value, do you see the slope? The slope, the change is equal slope. The slope of this line is 0. The slope of this line is 0.
Yes,
The
sir.
rate of change at this point, at this 0, is equal to 0. Okay. These points, look, when you differentiate this, so when you do d by dx of x square, you got something like 2x. Okay. If this slope is equal to 0, what did it tell you? So it tells you an important thing. It gives you a stable point. Like there is no rate of change, there is no change in sense change, there is no change there at that point. So this can be three things. It can be either minimum point, this can be maximum point, or the other point that I said, this can be saddle point. Okay, so if you see here, we have a minimum point. So if you otherwise have like this, if you have a graph like this is negative x square or something, negative x square, this will be equation. So at this point, do you see the slope is equal to 0 again? Do you see it?
Yes, sir.
If you see, the slope is 0 uh, at this point. So what I'm telling you is that when you get a derivative of a function is equal to 0 at some point, let's suppose that point is, we write that like this: derivative of f raised by x at x is equal to some point p. If it is 0, so we call this point a stable point. This is a stable point. The stable point can be the minima, it can be at the minimum value, it can be the maxima, it can be the maximum value, or it can be a saddle point. Saddle point I have shown you, which is sort of stable in one direction, and if you like give it a pick at one direction, it will fall. If you just give it a lot of perturbation in one direction, it will rise. So I'll again come to the saddle point, don't think about this much though. So here it will be a minima or a maxima that time. So if you just see the first derivative, okay. So what if I take the second derivative? Okay, what if I take the second derivative now? So I had x square, d by dx of x square. So it was 2x. I know that x is equal to 0, this function attains a stable point. But I don't know if it is a minimum or a maximum. So if I take double derivative now, d by dx square of x square. So that will be x. That will be 2, sorry. That will not be x, that will be 2, because this x will be gone. Now you see that this 2 is positive. If the double derivative is positive, then we have what is called as minima. We will have a minimum point. So if I told you that d by dx of x square at x is equal to 0 is equal to 0, that means 0 point is some stable point. Now I want to see if it is a maxima or a minima. So what will you do? You will take the double derivative of x square. That will be equal to 2. This 2 is greater than 0. So that means it is a minima. Okay. Let's suppose we had this minus x square. So what is the graph of minus x? It's like this. Minus x square is graph like this. So this is minus x square. So what if I take the derivative of minus x square with respect to x? This will give me minus 2x. So if now I know that at x is equal to 0, this is equal to 0. Okay, this slope is equal to 0 when I put x is equal to 0. So if I see double derivative of this minus x square, that's equal to minus 2, which is less than 0, then guaranteed we'll have a maxima. So this point is a maxima, then this point is a maxima. So here this point is a minima. This point is a minima. Okay, coming back to the Desmos, I'll show you there, so you guys will get a feel of this. So I'll again drop some graphs. This is my x square, which I showed you earlier. This is my x square. So here, if you see this point, so you know that for this point, this d by dx of x square is basically equal to 0. So this is a stable point. Now we have to confirm it is a minima or maxima. So by eyeballing, you can see here. What is this? Is it a minima or maxima? What is it?
Min- the minima.
Yes, it's a minima because you can see it directly over here. But there will be a function will be so complicated which you cannot even sort of comprehend, and you cannot draw them on the paper. So for that you have to say whether it's a minima or maxima. So you won't draw all the time. So what will you do is you will do like this. So you will say d by dx when you take double derivative of x square. So this is equal to 2. So this is basically greater than 0. So guaranteed this function has a minima. Okay, let me again change this graph a bit. So x square plus 2x plus 13, let's suppose plus 1. So this is 1, this is the graph. Okay, so this is the graph. Here it has a minima onto this point. If you see, oh sorry. So what I'm saying is, I'm saying if you see this graph, I have a graph of, this is the graph, x square plus 2x plus 1. I think it's visible over here. So now if you see this graph, the graph looks like this. Okay, so now the minima point is like at minus 1. So now to confirm this, let's see. So the equation is x square plus 2x plus 1. Let's see if mathematics agrees. So this is our function. So let's take df by dx. So what will be df by dx? This will be 2x plus 2. So this is the first derivative. So where will be the value 0? Now if I put minus 1 over here, so this equation will become 0. So 2 into minus 1 plus 2, this is equal to minus 2 plus 2, this is equal to 0. That's what the graph showed. If you see this graph, this point it's minus 1, isn't it? This point.
Yes, sir.
Are you able to see? That's what mathematics said. Mathematics said there is minus 1, which is stable point. At minus 1, it is stable. But now I need to confirm is the minima or maxima. So for that I should take double derivative of this. I should take double derivative. So this double derivative will be basically equal to 2 if I'm right. So it will be 2x first and then it will be 2. Yeah, it will be 2. So this is positive greater than 0. So this will be, I can make a complicated function, maybe something x cube neither has minima nor maxima. Let's write x square minus x plus cos of x. You can just write the things and you can just try with the tool. I don't want to waste the time of yours. So what I'm telling you, you just draw a function onto the plane, onto this 2D surface, and then you see what is the what does the minima and maxima are there, and then what you do is you just try to see if the mathematics that you are deriving agrees with the graph that you are looking. I'll just plug in the charger. So what I'm telling you is, I'm telling you that just see this Desmos calculator, and try to graph different functions and find the first stable point. The first thing is you'll find the stable point. What is the stable point? When the derivative is equal to 0. When this first derivative becomes 0. So if you want to see if it is minima, if it is maxima, or if it's a saddle point, we'll see the saddle point separately. Minima maxima initially says the derivative should be the second derivative. This is first derivative, and this is second derivative. SD. It should be, if it is positive, it is minima. If it is negative, it's maxima. Okay, so this is the story about the double derivatives. Am I clear with this?
Yes, sir.
Now if you know the significance of this double derivatives, and you also know that there can be functions which can have multivariate, which will be multivariate in nature. They'll have multiple variables. So we also need to see the stable points for these functions. We also need to see that, and for that you can take the partial derivatives first in order to find the direction, in order to find the rate of change in different directions. And now in order to see like what points do exist, like for example whatever we did in the 1D case, we want to do it in 2D 3D case. So for that we have what is called as Hessian matrix. So what is that? So if you have a function, you take the partial derivative. You have a vector, you take partial derivative. So for example, you'll take d by df of x1. Okay, then you will take, let's suppose, d by dx of x2. You'll take d by dx2 of f. Like you'll take second derivative of. You'll take the gradient of, or maybe you'll take partial derivative of f with respect to x2. And similarly, you'll take partial derivative of f with respect to xn. Okay, this is the thing. So what is the in Hessian matrix is you take double derivative now, but not with respect to only x1. Now you take double derivative of this same function with respect to, let's suppose, x1 first, then d by df dx1 x2. Okay, now again df by dx1 dx3 and things like this, x1 till xn. Okay, and in the similar fashion here you will do, this is dx1. Now you're taking double derivatives, but what you are doing is you are making sure that you take every possible combination sort of thing. So if you have x1 and till xn, so how many combinations will be there? So there will be n square combinations, because now you take x1 x2, you take combination of x1 x1 x2 x3 and things like xn, and then you take x1 x you also take x2 x3 or x2 x4 and things like that. That's what is written here. If you see this matrix, so if you just fill this one now, so this will be curl f by dx2 x2. Okay, this will be curl x1, no, x2, sorry. So this will be, so this is like we are starting with x1 x2, and here it will be x1 curl of x1. Here it will be again going the similar way back. Here it will be df by curl of x2 xn. At the end we'll have xn xn. Okay, now it's a matrix. Do you see it's a matrix? Here they'll have particular values. These things will be some values, some scalar values, if you ask me. So this is what we call as Hessian matrix. So what is special about this matrix? The special thing about this matrix is that it captures the double derivatives. Like it captures the double derivative x1 with respect to x1, then x1 with respect to x2 also. So you do derivate the first time with x1, and the second time with x2, in the similar fashion. Now this is a really good matrix. This matrix, if you see, is a symmetric matrix. Is it symmetric? Yes, it is. Why? You see this entry, you see this entry. Equal. Okay. So if you see these parallel entries, you will see that this matrix, Hessian matrix, is this. If this Hessian matrix is represented by H, so this H is equal to H transpose. Okay, if you have these real values now, you know what is special about this matrix again? If you have the real entries now, it is a positive semi-definite matrix. Positive semi-definite. Okay, I told you about I told you what is so special about symmetric matrix. What is special about positive symmetric? If you don't know them, go back to the lectures where we discussed about the algebra, and we discussed about these stuff. They are positive semi-definite matrices and they are special matrices. Okay, and you can think this as gradient of gradients. This is as gradient of gradients. Okay, am I clear with this?
Yes, sir.
Am I clear with this Hessian matrix?
Yes, sir.
Nice. So now what we'll do is we are dealing with what is called as convex functions. Okay, so we'll be dealing with what is called as convexity. These are requisites which are required. This mathematical background is required when you solve the optimizations. Okay, so that's the reason I'm showing you all of this stuff so that you understand it really well. Okay, now coming to the convexity. So what is the convexity? So we'll see first what is a convex set. What is a convex set? Okay, so this is what we'll see. So for example, if we have a set of points and that they are described something like this in the real world, something like this. Okay, so we'll say this set is convex if we take any 2 points within the set, any two values within the set. We take these 2 points. So if we join them by a line, so all the points that are on the line, they should belong to this set also. They should belong to this set. Then we'll call it convex. So again, coming up, what is the convex set? So if I have this convex, this for example set of points. So what I'm telling you is that I'll take any two arbitrary points. I took this point and this point. So if I join them by this line, this red line, if I join them by this red line, so all the points that are on this red line, the points on the red line are, this is a point on the red line, this is a point on the red line, this is a point on the red line. There are infinite points on the red line. So all these points should belong to this set. Then it is a convex set. So do you feel, is this a convex set? Is this a convex set? Umar, Jahangir, Amir, what do you think?
So don't know.
So have you understood what the definition of convex set? I told you that you take any 2 points. So all the points on the line, on this red line, should lie within the set. So you see the boundary of the set is over here. So this is the boundary. This is the boundary of the set. So do you feel this blue point, this point is not lying within the set? This is a non-convex set.
Yes.
This is non-convex then, because these 2 points they lie within the set. I took them and joined them in line, but the points on the line they don't. But if we have a set like this, if we have a set circle, do you think it's a convex set?
Yes, sir.
Why take any 2 points? For example, I'll take this point, I'll take this point. If I join them by a line, all the points that are in the line that they belong inside to this circle. So this is a convex set. Okay, so if I have to write the formal definition, how I'll write it. Now see how I'll formalize the English statements. See, so what I'll say is a set X, let's call this set X. A set X is convex if and only if, this is a if and only if the line segment joining any 2 points, any two arbitrary points, joining any 2 points, okay. If we have any line join any 2 points, let's say these points are X and Y which belong to X, and if a line segment is joining them, so it remains an X. So how I write mathematically? So I'll say for all X comma Y, so all the points which I take, any arbitrary point X and any arbitrary point Y, so which belongs to this set X. Okay, so if I have to join them, so if I have to make a line segment, so you know the equation of line. If I join these 2 points, so what we'll do is we'll say alpha times X plus 1 minus alpha times Y. This represents the represents line, but alpha should be, the value of alpha should belong from 0 to 1. So this is the line, this is the representation, this is the equation of this line. I have taught you the equations of line. So this, or the values in this should basically lie within the X. So this should be within the X. So this is what I mathematically wrote. Initially I said that if you join 2 points, okay, they should, all the points on the line should lie within the line. That is, the line should be inside this X. But what I am saying mathematically, for all X comma Y, this means all the points that belong to X comma Y. You take only 2 points, X and Y. You join the line. So this is the line joining them. Line joining these x and y. Okay, so it should belong to x. So it should be within this. So this is called a convex set. Is it clear?
Yes, sir.
Okay, if this is clear, then we have a convex hull. So convex hull basically, I without any definition, I'll tell you that. For example, if you have a lot of points in the set like this, okay, if you have points like this in the set, so what you do is you take nail and you have nails on that this, and then you sort of wrap around the ribbon or something, or maybe thread. So this will look like this, something like this. Don't you feel if you have these nails onto and you just put a rubber band on it, so this rubber band will sort of cover this. Maybe there will be some points inside like this. So if you want to cover the exterior boundary, or this is called as convex hull. This is that convex hull. Did you understand the convex hull? So if you have a lot of points, you sort of cover them in such a way so that you cover all the elements in that. This is convex hull. Why is it convex hull? You know now why it's convex. Because if you take any 2 points, let's suppose I'll take this point, I'll take this point, I'll drop a line. You know that it's inside this line. So this is convex. So if you take these point, if you take this point, and if you take this point, you draw a line. This is within that set. This is why that's the reason it's called convex hull. But it's convex and it's a sort of hull-like thing. Now the main thing remains that what is a convex function? So because we have a function now, we have to see if the function is convex. So we have to see if the function is convex. Okay. What are convex functions? This is what we have to deal with. So there are a lot of definitions of this convex function, but the thing that the definition I'll give you, this is called as Jensen's inequality. Jensen's inequality. So what it says is, first I'll tell it in words and I'll show it, then I'll write it mathematically, because now you have the bag, you will easily understand it. So let's suppose I have a function like this. This is my function. Okay, there can be a function like this. Let's suppose some cos theta plus 1, something like this. This is my function. So what Jensen said, that he said if you pick any 2 points, let's suppose I'll pick this point, I'll pick this point. I chose these 2 points. Now again, if you draw the line, onto this point, if you find the values of that line, they lie below this function. For example, here the value of function is this. Here the value of function at this point is this, and value of the line is it here. So here you see it is less than this. So this won't be a convex function. So always what will be a convex function? I'll show you. So if a function is like this, so now you take any 2 points. I'll take this point, I'll take this point. The value of the points on this line is always greater than or equal to the value of that function. Let's suppose I'll take this point. The value of this point of the function is this much, and the value of this point on the line is this much. So the value of the point on the line is always greater or equal to the value of the function. So this function is convex. This is not convex. This is called a Jensen's inequality. So if you have the point x, I have 2 points x and y. So what I'm telling you, if you join them by a line, so there will be points lying on this line. A lot of points will be on the lying on the line. So I'm saying all these points are lying on lying on the line. They should have the value greater or equal to that of the function. Okay, you can see that here. Take any point over here. So all these points over here have less values than the values on the line. Is it clear? Like, is it clear verbally at least? What is the convex function?
Yes, sir.
So how you can write it mathematically is that you can write, if you take function of this, the function is basically this. So you can represent the function by this: alpha of x plus, so alpha of x plus 1 minus alpha of y, and this is like, let's suppose in two variables x and y. So alpha x plus 1 minus alpha of y, this should be less than equal to, what should be less than equal to f of alpha of f of x, okay, plus 1 minus alpha of f of y. Okay, this is the value, this is the value of the function. It should be always less. Okay, so then we call that function as a convex function. This is called as Jensen's inequality. I'll write it in a better way. So f of alpha into x plus 1 minus alpha into y is less than equal to alpha of f of x plus 1 minus alpha of f of y. This is called as Jensen's inequality. Okay, so such functions we call them as convex functions. So if you have a function, so if you see it over here, so this line's value is always greater than this function's value. So that's what I'm saying is, so this is the function, so it should always, these values should always be less than or equal to what are the values over there. Is it clear? So but here alpha should belong to 0 comma 1. The value should be within this. Is the Jensen inequality clear? So how to identify this convex function? Is it clear now?
Yes, sir.
There are a lot of other definitions, but I won't go into that. The definition of this Hessian matrix, or the definition of like what is called as epigraph and something like that. But this definition is more than enough. Now, if you are given a function, you are given a function, and you are told if it is convex or not. So first thing you should check it, but it's a very difficult task. So what are the things? So there are some blocks, some famous functions which are convex. So if you see parts of these functions, you can decide. Let's suppose this A transpose x plus b. This is the convex function, and x log x for x is greater than 0 is a convex function. X transpose px, where for all p is greater than 0, it is a, if you remember, this is called energy equation. We have also covered this in algebra. So this is also a convex equation. So any norm equation like this is a convex equation. So if we have maximum of max of x1 x2, so this also is a function. So this is also a convex equation, but this is for infinity norm. These are some famous convex functions. So if you have a function and you have to decide, for example, if it's a convex function, you have to look if there are some parts in that. Composition of convex functions is also a convex function. If you have like composition of a function, so that way you can see if it's a convex or not. For example, if I have an example like this, I read an example, you have to see if it's a convex or not. So let's suppose we have x minus y whole square divided by 1 minus max of x comma y, and this is minimum of x y. So is it a convex function? So what I'll do is I'll break it. So here let's break it like this. So I'll break it in division. So it is divided. The first part is it is squared, and then what is squared? X minus y is squared. So I'll write it with blue. So as to, so initially we have division. So I'll say we are dividing something. So we are dividing something by something. What is this something? So it is getting squared. So this, what is getting squared? X minus y thing is getting squared. Okay, so what is in the denominator? It is 1 minus something. What is this something again? It is max of x comma y. Okay, so now if we want to see if it is a convex function, now you can see that over here this max is a convex function, because we have written that over here. Max is a convex function. Now this again is a convex function. This is not square. This is a convex function. This is a convex function. Okay, and now I think this is a concave function. This 1 minus is a concave function. This 1 minus something, it makes concave function. Okay, so now you have parts. If we had till only till here, and if it was composition function, we can say the composition of this is basically a convex function. Okay, is it clear how to see? Like you have to just remember this is a convex, this is a and functions will be a combination of these. So if a function is combination of this, composition of this, we'll say that it's a convex function. Is the convexity clear at least to some extent? What convexity means?
Yes, sir.
Nice.
Nice.
So
Yes.
the next topic that we have to cover is called as Taylor's series. Okay, so I'll just give a brief overview of Taylor's series, and I'll take that in the next class because we're left with very less time. So maybe I'll stop it here, otherwise it'll again stretch. I'll just stop the recording.